Okay, I thought we could try another integral today. We have something here from MIT 2011, problem 14. We have the integral of dx over x squared times x to the fourth plus 1 to the 3/4. And at first, there seems like there's quite a few problems here because we're not that used to dealing with a fourth power, and then we have a 3/4 here. Looks kind of complicated, but then I was thinking maybe this is something where trig substitution might just work very nicely. And typically when we have if this was x squared plus 1, we would use a trig substitution for tangent. And so let's just try the same thing and see how it goes. And what I want to do for my substitution, I'm going to call x the square root of tan t, just because x squared is going to be tan of t, which is going to give us a value for this and something we can use for this. And while we're at it, why don't I just solve for t using the inverse? So we'll say t is going to be tan inverse x squared. Then we'll take a derivative here. So for our dt value, the derivative of arctan is going to be 1 over this input squared. So we're going to have x to the fourth plus 1. But then we're going to need the chain rule here. This is going to give us a 2x dx. But we want to get this thing in terms of t. We'll take a reciprocal here. So our x to the fourth plus 1, that's going to give us tan squared t plus 1. And 2x is going to be 2 square root of tan t. Then one other thing we can do, there's an identity for tan squared t plus 1. That's just the same thing as secant squared. So we're going to have secant squared t over 2 square root of tan t. Okay, now we have everything we need. We'll make the substitution. So for dx, we're going to have this expression over here. We'll have our secant squared t dt. Let's not forget this in the denominator. We're going to have 2 square root of tan t. For x squared, we're going to have a tan t over here. Now this thing, this is going to be, again, this here is going to actually be tan squared t plus 1, but we already found the tan squared t plus 1 is secant squared. Then I'm just going to do some cleanup. I'm going to bring this 2 out front, so we're going to have a half here. Tan t times tan t to the half is going to be tan to the 3/2. So the exponent here is going to be 2 times 3/4, which is 3/2. But then with exponent rules, we have a 2 power in the numerator, 3/2 here. When we divide that, we subtract the power. And so we're going to have a secant 1/2 t in the numerator. Next what I'm going to do is let's rewrite this in terms of sines and cosines so I can get some more cancellation and simplification. So secant is 1 over cosine. So we have 1 over cosine 1/2 t, tan of 3/2 is sine over cosine. So we're going to have, I'm just going to, because it's in the denominator, we'll flip it. So we're going to have sine 3/2 t here, and we'll have cosine 3/2 t in the numerator. Then with another rewrite, so here 1/2 is going to cancel with 3/2 cosine. We're just going to have cosine of t in the numerator. And then here, then the denominator, we're still going to have our sine 3/2 t. And then here, we're in good shape for a u substitution. So I'm just going to make my u substitution for sine. And then that's going to be perfect because we have our du exactly in the numerator. So that's going to be cosine t dt. So we're going to have our du. And then here, this is going to be just u to the minus 3/2 because it's in the denominator. Then I'm just going to integrate. U to the minus 3/2 is going to be u to the minus 1/2. But then we're going to need power rule. Minus 2. So we're going to have minus 1 over the square root of u, which is just sine t. Okay, and at this point we're almost done. We just need to get it back into x. We have it in t. And so in order to get this back into x, what I can do is draw my triangle, because we'll work with this expression right here. So drawing a right triangle, we're going to have our angle t, and then this can be looked at as like x squared over 1. So we'll have opposite over adjacent, x squared over 1. And it's easy to find the hypotenuse, just going to be a squared plus b, the square root of a squared plus b squared. So this is just going to be the square root of x, this squared, which is x to the fourth plus 1 squared. And so then for sine of t, we just want opposite over hypotenuse, which is going to be x squared over square root of x to the fourth plus 1. Then within this, let's just draw a big square root because we've got a lot going on here. So in here, for our sine of t, we're going to have x squared over x to the fourth plus 1. And then what I'm going to do to just clean this up, let's write x to the fourth plus 1 in the we'll bring it into the numerator, but it's within 2 square roots. So like a half times a half, and so the power on this is going to be 1/4. And then here I'm just going to leave this like this for the moment. And then here, okay, the square root of x squared, I could just write this as x and be done. That's maybe probably what I would do, but I want to get this to look like MIT's solution. So they went the other way. What they did in this solution is instead of getting the square root of this, they actually took it up a notch and wrote this as x to the fourth to the 1/4, just to make it clear, to match this power that we have in the numerator. And then now that the powers are the same, what we can do is we can put it under one exponent, divide this into this, so we're going to have x to the fourth divided into x to the fourth. We're going to have 1 plus x to the minus 4, all to the 1/4. And that's it. That's going to be the final solution, and that's going to match what's in the MIT solution key. So there's kind of a lot of steps for a trig sub problem, but still not too bad. So thanks everyone for watching. Take care.